Motion analysis software determines the position, velocity, and acceleration of objects in a high-speed or low-speed image sequence, and it does this for most conventional digital image formats. It can also import any time-based digital data, such as accelerometer or strain gauge. This data can then be combined with the position data in the graphs and spreadsheets. Once the analysis is complete, the software allows you to see the images, the graphs, and the spreadsheet data synchronized, and thus helps you to visualize the event. On this page you can see the combination of images, graphs, and spreadsheets and how they are synchronized together, showing things like positions, angles, and the head contour. If you are starting on a motion analysis project, you should remember that these 7 steps are necessary in order to get the best results. First, you need to select the approach to the test: a 2D test with 1 image, a 3D test with 2 synchronized images sequenced, or a 6 degree of freedom analysis of a rigid body using 1 or more cameras. Next, you need to select the targets in the image that you're going to track. This will be covered in detail later. Then you need to select the correct tracking algorithms to match the targets you will be using in the image. You need to determine what data, if any, needs to be imported to combine with the image data. Most importantly, you need to determine how you can set up your scaling. Finally, you need to set the camera up to get a good image of the events, noting that if you have a high frequency event, you may need a higher frame rate than that which just gets you a good image. You may also need to perform lens calibration to remove radial distortion if there is any significant fisheye effect in your lenses. Each of these will be covered in more detail. Starting with the first of those items, the 2-dimensional analysis will be accurate if all motion that you're tracking occurs in 1 or more definable planes. The 3-dimensional analysis with 2 cameras provides an accurate position of any object anytime, anywhere, as long as it can be seen by both cameras simultaneously. The 6 degrees of freedom analysis applies only to a rigid body that is not deformed during the test, and for which you have a survey of 6 or more points on the body. This survey can be carried out by a TEMA accessory called static. This slide shows a 2-dimensional analysis of a sled test using 2 parallel planes. The first plane is the one in which the sled moves, and the second is the one in which the scaling targets on the wall are behind the sled. The scale is set on those targets on the wall, and the distance of the sled and of those targets from the camera must be known and entered into the program so as to define the 2 planes. This slide shows a 3-dimensional analysis of the pointer dropping onto the table using 2 cameras which both see the pointer and which are synchronized in time. To perform a 3D analysis, the program needs to know the position and orientation of both cameras. And there are 3 ways to do this, and these will be covered later in detail, but in summary, the first option requires a survey of 6 targets in the field of view, and the coordinate system will then be based on the coordinate system used in the survey. The second method uses 6 points in the image, and it only requires that you know the distance between 2 of the points. However, the coordinate system is based on the center of the sensor of one of the cameras. The third option is to use a wand, which will be described later, and all that is needed is to wave the wand in front of the camera. However, again, the coordinate system is based on the center of the sensor of one of the cameras. So in the second 2 methods described, we need to have something in the field of view which will allow us to redefine the coordinate system so that it makes the test output readily usable. This closer view of the table onto which the pointer is dropping shows the 3 points we have chosen so that we can define a new coordinate system. Point F is the XYZ 0. The addition of point C defines the x-axis, and the third point on the table defines the xy plane. The dimensional location of these points is not needed. This is a 6 degree of freedom test in which the rigid body is the helmet. The targets on the helmet need to have been surveyed. One of these points, in this case the point 100, is the XYZ 0 point in the first frame. All motion in subsequent frames is based from this point. The roll, pitch and yaw angles are derived from those used in the helmet survey. The static program will allow you to take images from all around the rigid body and develop this survey using only one dimension, the distance between 2 points on that body. Motion analysis requires features in the image that can be tracked. There are three main ways to do this. The most common is the correlation, which takes any feature in the image and looks for that feature in the next frame. Accuracy with this method is approximately 1 pixel. The second method uses the quadrant target and focuses on the crosshairs. This method can get down to 1/10 of a pixel accuracy. A third method is to use the grayscale difference seen crossing the boundary of an object. In this case we are showing a light airbag against a dark background. The output is the contour of the airbag, which contrasts with the background. When talking about accuracy, we can quote this in pixels, but for a specific project this has to be converted into real units by dividing the field of view by the number of pixels in the sensor which produced that field of view. The software can produce graphs and spreadsheets documenting the position, velocity and acceleration of the objects. In addition, digital data from sources such as strain gauges and accelerometers can be imported and added to these graphs and spreadsheets. The data can be generated at frequencies other than the frame rate of the camera, but there must be a common digital time base or a feature such as a flash in the image and a marker in the digital file that provide a synchronizing point in time. This also assumes that the frame rate of the camera and the digitizing frequency of the imported data are accurately known. The three basic approaches, 2D, 3D and 6 degrees of freedom, all have different approaches to scaling. For 2D, the motion must be in definable planes, and in one of those planes there must be 2 points to provide scaling. The position data is then defined in the XY coordinates based on the bottom left-hand corner of the image. The base for the coordinate system can be moved during analysis to any other point in the image, static or dynamic, provided that that point has been tracked. For 3D motion, as explained earlier, the scaling is set up when the position and orientation of the cameras is determined. Again, the base for the coordinate system can be moved using static or dynamic points which are tracked in the image. Here you can see the wand that is used in the third method discussed earlier for setting up a 3D system. Scaling is provided by the dimensions of the wand. The 6 degree of freedom motion scaling is set up by the survey of the rigid body, and the coordinate system is based on the initial position of one of the points on the body. The body can move in any direction or plane, and the results will be valid. The coordinate systems cannot be moved during analysis, but there are options in the more advanced TrackEye program that will allow this to be done. If the image sequence has a high frequency motion in it, it may not be enough to get just a frame rate and exposure fast enough to give a clear, unblurred image. It may be necessary to go to a higher frame rate to capture enough detail. For instance, the motion could be sinusoidal. This graph illustrates how if the motion is captured at less than about 10 times the frequency of that motion, then the resulting data will not produce a sinusoidal plot, but moreover could show some form of beat frequency other than the original motion. If you are working with lenses with short focal lengths and have any degree of the fisheye effect, then you may need to calibrate the lens to remove this radial distortion. Any other distortion will also be removed. To do this, take the digital file provided, print it and hang it on a flat vertical surface, then using the camera lens pair that you are using for motion analysis imaging, take at least 6 frames, either still or movie, from 6 different angles by tracking the 4 major targets in the image. The radial distortion can be calculated and then removed from the subsequent motion analysis calculation. This shows a very thorough example of how to photograph the target. Now we're going to go right back to the beginning here and see the 7 steps you need to take to get good results from any motion analysis program. First, select the approach for the test, 2D, 3D, or 6 degrees of freedom. Select the target types you'll use and the corresponding algorithms, and if necessary, add targets to the test articles. Determine whether you are going to import other digital data, and if so, how you are going to synchronize it with the images. Determine how you can set up your scaling and coordinate system to get results in terms useful for your project. Make sure you have a good clear image and that the frame rate is high enough to capture any high-frequency events in the image sequence. If necessary, perform a lens calibration